So hello everyone again, this is lecture 1 part 2 of ray optics and optical instruments. In the previous part we just started with the introduction of why is the ray optics necessary, why was the difference between the ray optics and the wave optics, and a basic discussion of what is center of curvature, what is pole, what is principal axis, etc. Today let us start with the sign conventions and move on with the further discussions of this chapter only. So I am Sameer Lavankar, let us begin our discussion. Okay, so the course outline, we have already covered the introduction part of this ray optics, and right now we are on the second part, that is the reflection of light by spherical mirrors. Okay, so these all things were being explained in the previous lecture only. So this is a pole, this is an optical center, and there is something called as principal axis. Okay, let us move on with the sign convention now. So to derive the relevant formula for reflection by spherical mirrors and refraction by spherical lenses, we must first adopt a sign convention for measuring distances. What are the distances being talked about here? There is something called as object distance. There is something called as image distance. There is something called as height of object. There is something called as, let me write it here, height of image. There is something called as, another concept, just for telling you the concept, there is something called as magnification. So to deal with each of these concepts written here, what we do is we perform or we adopt a sign convention, so that everything which is understand can be interpreted by us, how it is it visible or not, it is real, virtual, inverted, etc. Okay, so let us start. So to derive the relevant formula for reflection by spherical mirrors and refraction by spherical lenses, we must first adopt a sign convention for measuring distances. Okay. Next is we shall follow the Cartesian sign convention. So what is this Cartesian sign convention? So according to this convention, all distances are measured from the pole of the mirror. So which is the pole here? So this is the pole here. Everything has been measured from the pole of the mirror, or the optical center of the lens. So basically if it would have been a lens, so there would have been an optical center and everything would have been observed or measured from the optical center of the lens only. Next, so this thing has been explained. Next is the distances measured in the same direction as the incident light are taken as positive, and so please remember, please look over here carefully now. So distances measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light is taken as negative. So let us suppose this is a direction of incident of light. Let us suppose we are moving in this direction, then this is in negative, and if you are moving in this direction, then these are taken as positive. Okay. So where was I? So distance measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light are taken as negative. Okay. So this thing has been explained. Next is the heights measured. Next is the heights measured along the upward in with respect to x axis and normal to the principal axis of the mirror or lens are taken as positive. So basically these height, as you can see, quite evident, from this point can be taken as positive and here it can be taken as negative. Okay. So this thing has been explained. So basically it is same for both mirror and lenses. Next is the height measured downward are taken as negative, quite evident. With a common accepted convention, it turns out that a single formula for spherical mirrors and a single formula for spherical lenses can handle all different cases. So that is the end of the sign convention. So just let me revise everything. Everything is being measured from the pole of the mirror, first of all, first thing. The next thing is that every distance which is in the direction of incidence of light is taken as positive, and every distance which is away from the direction of incidence of light or opposite to the direction of incidence of light is taken as negative. Next is for the height which is above the principal axis taken as positive, and the height which is below the principal axis is taken as negative. That is all. These are all the sign conventions. Now we will try to derive the two different equations. First the mirror equation, and after some lectures we will try to derive the lens equation. those two equations can be used for the complete entire of ray optics for your calculations. Okay, let us move on. So, before that just let me explain again, let me revise the concept of focal length, and there is something called as focal plane. So, what are these things, just observe and then we can move on with the derivation for the mirror equation. Okay. For the focal length of spherical mirrors, please make sure we are talking about the mirrors only, there is no concept of lens being added till now. Okay. So, figure shows what happens when a parallel beam of light is incident on a concave mirror. So, as you can see, this is a concave mirror for you and this is a convex mirror for you. Okay. So, we assume that the rays are para-axial. So, what is the meaning of para-axial? Please just understand here. So, they are incident at points close to the pole P, this is the pole P being talked about, and make small angles with the principal axis, So, these all angles which they are trying to make are very small, very small, as in even if we take the value sin theta, we take it approximately equal to tan theta, which we take approximately equal to theta. So, these all approximations can be understood, or which these approximations can be taken care if we take or we assume that the rays are para-axial. So, this is one of the assumptions which we take in our complete entirety of ray optics. Okay. So, we just assume that the rays are para-axial, that is they are incident at points close to the pole P of the mirror and make small angles with the principal axis. Okay. Next is the reflected rays converge at a point F, quite evident as you can see. So, these are all are the rays. So, by basic law of reflection, that is angle of incidence is equal to angle of reflection. So, basically this is the normal being formed here, normal being formed here, normal being formed here and normal being formed here. You can find that this is, let us say, this is the angle of incidence, this is the angle of reflection. So, basically everything after the incidence is happening, it is always incident at a single point, at a concurrent point. What is that point? So, that point is nothing but called as the focus of the mirror. Okay. So, the reflected rays converge at a point F on the principal axis. Yes, please make sure it is principal axis for you here, principal axis of a concave mirror, as you can see in figure A. For a convex mirror, the reflected rays appear to diverge from a point F. So, quite evident, as you can see, these points cannot just go through the mirror, it has to be diverged only. But if we just plot the points towards backwards, we can find that every point or every light of reflected ray is emerging from a virtual point called as the focus of the mirror or a point F. Okay, so for a convex mirror, the reflected rays appear to diverge from a point F on its principal axis. Quite evident, this is called as your principal axis. Okay. Next thing is, so the point F is called the principal focus of the mirror. So, please make sure, so just again a theory portion, what is this F point? F point is nothing but called as principal focus. Principal focus. Okay. So, if the parallel para-axial beam of light were incident making some angle with the principal axis, the reflected rays would converge from a point in a plane through F normal to the principal axis. Nothing, everything which has been explained here is being written in a single line. So, if the parallel para-axial beam of light were incident making some angle with the principal axis, as you can see, these all things were being understood as para-axial rays. So, these all things were para-axial rays, but sometime what would happen is, as you can see in this figure here. So, always the rays are not para-axial, that is not, they are not always parallel to the principal axis. What will happen in that sense? Does it always converge at point F only, or does it change, into some other point, or every incident light happens to attain a point which is not F? So, what actually happens is that the point just shifts. The point just shifts from its position and there is a new focal point or principal focus being formed, which is a little bit down. In this case, it can be any place in this plane here, depending upon the angle which the incidence light makes with the principal axis. So, if the parallel para-axial beam of light were incident making some angle with the principal axis, the reflected rays would converge. Quite evident, as you can see, that they would definitely converge, but from a point in a plane through f normal to the principal axis. So, if you make a normal to this portion here, if you make a normal to this portion here, then you can find that the new point f dash is lying on that focal plane only. So, this is called the focal plane of the mirror. So, just a new different thing, maybe you haven't understood this, or maybe you haven't learned this in your previous classes or discussions, but this is something called as focal plane. So, when it is necessary, it is only and only necessary when the light beams or the incidence lights are not paraaxial. What does it mean by paraaxial? Paraaxial just means that every beam of light or every ray of light is considered first of all to be parallel to the principal axis, and second is that the angle which it makes, this angle which it makes is very small, very small, as in we can consider sin theta approximately equal to tan theta approximately equal to theta. So, that is the end of the focal length discussion also. Let us move on. Okay, so now theory part or derivation part, in which you try to prove something, that is f is equal to capital R by 2. So, what is the distance f? F is nothing but this portion here, and what is capital R? Capital R is this portion here. So, we are just trying to prove that the focal length distance is nothing but half of the center of from the distance from center of curvature to the pole of the mirror. Okay, so let us try to derive this now. So, very easy discussion, just based on the assumption that the rays are paraaxial is being used here, and just derivation has been made. Okay. So, the first point is that distance between the focus f and the pole p of the mirror is called the focal length of the mirror, which is denoted by small f. Okay, so this thing has been understood. Next point is, we now show that f is equal to capital R by 2. What is R here? Capital R is the radius of curvature of the mirror. Capital R is radius of curvature of the mirror. Okay. So, let us derive this. So, geometry of reflection of an incident ray is shown in the figure. So, this has been shown in the figure. So, these basically is an incident ray. This basically is an incident ray here. Okay. So, this thing has been explained. Next is, let us see with the center of curvature of the mirror. Let us see with the center of curvature of the mirror. So, this is the center of curvature of the mirror. Next is, consider a ray parallel to the principal axis striking the mirror at M. So, please make sure these both lines are parallel here. So, first of all, we are understanding, or we are considering a ray parallel to the principal axis. So, this is parallel to the principal axis striking the mirror at M. So, it is striking at this point here. Next is, let CM be the perpendicular to the mirror at M. So, CM is the perpendicular, or it is the normal to the mirror at the point M. Okay. So, this thing has been explained. Next is, let theta be the angle of incidence, quite evident. So, this will be the angle theta, and because this is angle theta, which is angle I, which is equal to angle R, and this angle will also be equal to theta. Okay. So, this thing has been explained again. Let MD be the perpendicular from M on the principal axis. So, MD is the perpendicular. What does it mean by perpendicular? So, basically this angle is 90 degrees for you. Next is, as you can see, quite evident, angle MCP. So, it is MCP. So, this angle is theta, and angle MFP is 2 theta. Angle MFP, basically this angle is 2 theta. Why it is 2 theta? So, basically you are just using the mathematical formulation that these all things like this. So, this angle 2 theta is equal to this angle 2 theta here. Okay, so these all things are understood. Next is, now tan theta is equal to MD upon CD. Quite evident, as you can see from this triangle here. So, here tan theta is equal to MD upon CD. Next is, tan 2 theta is equal to MD upon FD. So, using this triangle here. MD upon FD. So, now just using this concept and the concept of paraaxial rays. So, now for small theta we can consider, which is true for paraaxial rays, tan theta approximately equal to theta, and tan 2 theta approximately equal to 2 theta. So, using these two equations we can write, first of all we can write theta is equal to MD upon CD, and we can write 2 theta is equal to MD upon FD. So, basically now what we can write, using this equation and using this equation as MD upon FD is equal to 2 into MD upon CD. Therefore, MD gets cancelled and we can find this as FD, which is equal to CD by 2. So, what is the FD distance here? This is that FD distance, and what is the CD distance here? This is the CD distance. Now, for the para-axial rays, this is an assumption that the theta angles are very small, and because these lights are very close to the principal axis, it is being understood, it can be assumed that this D point is very close to this P point. So, D and P can coincident, and hence we can find that FD can be approximately equal to FP. Similarly, CD can be approximately equal to CP by 2. Now, what is this FD distance? FD distance is nothing but the focal length. And what is the CP distance? CP distance is nothing but the radius. Therefore, we found that F is equal to capital R by 2. Hence, this is the derivation for the focal length, which is equal to half of the center of curvature or half of the radius of curvature. Okay. Not the center of curvature, the distance between center of curvature and the pole. Okay, so just read here. So, for small theta, which is true for para-axial rays, tan theta is approximately equal to theta, and also tan 2 theta is approximately equal to 2 theta. Therefore, above equation gives MD by CD is equal to 2 MD by FCD, or FD is equal to CD by 2, which we have derived here. So, this is same, which is FD is equal to CD by 2. Now, for small theta, the point D is very close to the point P, quite evident as the assumption. These all things are being explained only and only till the point is assumed that the ray of lights are para-axial rays. Okay. Therefore, capital FD is equal to small f, and CD is equal to capital R. Therefore, we can find that F is equal to R by 2. Hence, this is the assumption, or this is the derivation being made based on the assumption that the rays are para-axial rays. Okay, let us move on. So, if the rays emanating from a point actually meet at another point after reflection and on refraction, that point is called as image of the first point. Okay. So, what is an image of the first point? So, image of the first point is nothing but that if the ray, so let me just make it using a diagram. So, let us suppose this is the image like this. So, this is an object here. So, after some discussions we found that the image was of height this. So, if the image is being formed here, this is something the image is being formed, it is a real image. So, this is the basic definition which is being talked about here. So, this is basically what is called here. So, if the rays emanating from a point actually meet at another point, the rays emanating from a point actually meet at another point after reflection and on refraction, and that point is called as the image of the first point. So, this is nothing but, so this point is nothing but image of the first point. If we denote this as that object image or object of the object which is a point. Okay. So, these all things were being understood. So, let me stop it here only. After this, in the next lecture, I will make you understand the complete basic concepts of mirror equation, and we will try to derive the mirror equation. So, this is basically the mirror equation. So, let me derive in the next lecture. Let me stop it here only. So, thank you so much.